So lecture number 19, advanced main game loops. And just as a quick note beforehand, the material for all of these, not all of these slides, but some of these slides, especially where you see these little paper-looking cutout photos, these are from the optional textbook from the course, which is Game Programming Patterns. And so they talk about some things that I don't, and I talk about some things that they don't, but just realize that there is more there. There's more there if you want to look at it. And also that none of this stuff is required for the project. It's more so, oh, I actually need to think about this stuff when my game engine becomes more complicated, especially when we want to do something like, for example, separate or decouple the rendering from the game updates. And we'll talk about that. So in the beginning, when you started programming, maybe even before this course, maybe all the programming you've done so far, before you were looking at user interfaces or games, you're going to be writing console programs, right? So that's usually your first program that you learn how to write. So the structure of those programs typically have the following like main architecture, right? They're very, very simple, but they follow the structure, which is, okay, I'm going to run some initial code. Maybe that's like setting up some variables. And then maybe I also print some instructions to the screen. And so, for example, you know, you can think back to your first programming assignment ever. It was probably something like print hello world. Like that's the first one, right? But after that, it might be, oh, let's convert from Celsius to Fahrenheit or whatever units, right? So you're going to print out some instructions like, please enter a temperature in Celsius, and then you're going to wait for some input from the user, right? So you have the little blinking cursor there waiting for you to type in. You type in some number, and then once you get that user input, you store that somehow, probably in a variable, and then you continue on with the program code. And so you might convert it to something else, you might print it, you might store it in a file, whatever you want to do. So very, very, very simple type of program architecture, typically written in the console. And what I didn't put here was a while loop, right? So typically, you're not just going to run this program once. You're going to want to do more things with it, or do the same thing multiple times. And so what we had was a program structure something like this. So we have our main function, and that's all we're doing in this program is the main. And then we have some input where we're going, or some variable where we're going to store our input. Then we have this loop here that says like, oh, look at this. This is even a simpler example that I came up with. So enter a distance in feet. So we standard C out that. And then we can use C in. We actually didn't do that this year, but C in is kind of the opposite of standard out, or C out, which is input from the console. That's how you would grab that. So you take that, you put it into your input variable, and then you say, oh, do some calculation with that. So that is input times 12 inches. So this program really, really likes converting feet to inches, right? So much so that you can't even exit this program. It just does feet to inches forever and ever and ever. Now, I guess if you put in something that's not a number, it'll crash, right? So we would put in some other things like, okay, put in Q if you want to quit or whatever. But the main point here is that we have this structure, is that we want to do something initially. Oh, look, I have a slide on this. So maybe display some instructions to the user, and then while true, meaning until this program we've told it to quit, right? Or until it's done its job. We're going to wait for some user input, and the important thing here is that, you know, these early programs that you write, all of that user input is called blocking input. You've heard of blocking versus non-blocking, of course, yeah. So this blocking user input, essentially, the program does not continue until you give it that input, right? And so that's very important and a distinction from video games, which we'll talk about in a bit. And then you do something interesting with that input. So you convert it, you display it, you put it on a website, you do whatever. And then you display more instructions or quit or whatever, right? So you decide somehow whether or not you want to continue in this loop, or you want to exit that loop or exit the program or go on to something else. But this is generally the main structure of most programs like this. Then at some point, you learned about GUIs, or graphical user interfaces. Even modern GUIs follow the same basic structure as this, since nothing in the GUI changes unless the user inputs some values. Now, for example, let's say we make a word processor, right? And I know that this is not how like a modern Microsoft Word will work. Like, for example, it might have a blinking cursor. It might have Clippy down in the bottom right doing some stuff. But this is like, you know, a very basic, most simple possible word processor where it literally does nothing until you start typing into it. So you're going to display some current document or a blank document, and then it's not really going to do anything else until you do something to that document. Like you could type it in, you could select some text, you could change the font size, whatever. And then it would handle that user input somehow and then repeat, right? So here, it's the same structure. It's the same overall architecture for that. So display some initial GUI on the screen, whether or not that contains instructions or not. So this is that initial part where you set everything up and then you display it. And then you poll the user for input events. And if there were user input events, then you update whatever internal variables based on the input events. So for example, if I have some text box and I've typed into it, I'm going to add those character keystrokes to the text box, change the font, whatever I have to do. And then based on the update of those variables, I'm going to update the user interface somehow. So very, very similar to what we just did for a console program, but now it's just in a user interface. And of course, this ignores all sorts of things about threading, etc. So this is just like single-threaded continuous code. Now when we move on to games, what happens is that unlike those other programs, the games keep moving even when you don't type anything in, right? So far we've been talking about architectures for these like blocking input type systems. And now we have something that is typically non-blocking. So the game, Mario, if you're playing Mario, the Goombas are going to still walk into you and kill you if you don't input anything, right? So something is happening even if you're not doing input. So the game won't be paused just because the user isn't doing anything. Now I actually have played a game, I can't remember it. What was it called? Super Hot? Is that the, yeah, so that in that game, the game literally doesn't progress until you put in inputs, so you can kind of think about what you have to do. It's like a really interesting game architecture. But, you know, other than stuff like that, games usually are just progressing, even if you're not putting in anything. So the clock keeps ticking, NPCs keeps moving, animations keep animating, etc., even if you're not typing anything in. And so the key here is that we don't wait for some user input. It's not blocking like it was in those other examples. Of course, you know, you can have a GUI that doesn't block as well. I'm not saying that games are the only things that don't block. I just cherry-picked those other two examples of blocking input. So with a game, you're going to display some initial screen or user interface or menu or whatever to the user. Then the important part here is that you're going to process the user input if any exists, right? So we've been doing this so far in our course. We have that little loop in the game engine that goes over any events that have happened, and then we do things based on those events. Then we are going to update the internal game simulation by one step, and then we're going to render the game screen, right? So user input, update of the game state, and then render that game state. And so in a little more programmer-friendly manner, we have these functions here. So we process the user input, then we use that input to update our internal game state. So, okay, we read, all right, the user pressed the right key, and so the player is going to move to the right by some amount. Oh, look, there was a collision with a wall, so we pushed him back out of the wall. And then based on the result of that update, we're going to take the game state, we're going to draw it to the screen. Okay, why isn't this the first lecture of the course, you say? Well, we'll get to a little bit more complicated stuff in a bit. And that update function can be really complicated, right? And the update function for our game actually contains the user input code, right? The user input and the rendering down here. Now, we decoupled the actual parsing of raw user input from actions in our game engine, but I just left this here just to show you that, yes, we are actually looking at that user input. So we have the process input, we have the update where we update the entity manager and call all the systems, And then down here, we take the result of that and we draw it to the screen. Okay, so you know all of this, but that's the game loop that we've been establishing so far. Now, some of the rest of the stuff we have talked about, some of it we haven't talked about. But the game loop speed is very, very important. And when programs use blocking input, they can run the main loop at any speed that they want, right? This can be like running 1 trillion times a second or once per second. Doesn't really matter because you're just waiting for the user input. So it's going to be blocking it. It literally can't go anywhere until you've done that. And so since it's limited by the user input speed, it doesn't matter. We don't need to care about the speed of that while loop. We don't need to control it. We don't need to worry about it. So with non-blocking input in our main game loop, we now need to talk about how fast this loop is running. All right. So since each update advances the game world by the same amount on each call. Now, I'm not saying that every game engine does this, but our game engine currently does do this, right? Like, let's say the speed is 5, then Mega Man moves to the right or Link moves to the right by 5. And so if it's updated by the same amount each call, then what's going to happen is, okay, if my main loop is running faster on one machine than another, then the gameplay is actually going to be affected. Right? If I'm running on one machine at 100 frames per second and another machine at 30 frames per second, that faster machine, the game is playing 3.3 times as fast, right? And that's not something desirable in video games. And so the game world clock is going to tick forward by 1, but the player's real world clock ticks forward at a different speed. What does that mean? Well, it means everyone in this room has a different speed computer, probably, right? Just by a minor amount. And so if we run our game engine with no SFML frames per second cap, for example, each of your game engines, if you think of like the universe that Link is living in, the game engine clock that's ticking forward by on your machine is actually going at a different speed than someone else's machine. But all of your real-world clocks, the speed at which we experience the universe, unless you happen to be coding at the speed of light, right, is going to be the same. And so there's this difference between the relative speed of the clock on the wall and the clock in the game universe. And ideally, no matter what hardware you run on, that would be the same, right? Because you want your game experience to be the same on different hardware. Now, of course, you'd want something like, oh, if they have a fancy graphics card, maybe it will render smoother or something like that. But you basically want, you know, Mario or Link to be running at the same speed, bullets to be shooting at the same speed, etc. So how many game loop cycles are in 1 second, and we're talking about the game loop we just talked about, determines the game's frames per second count. Now, that's pretty obvious to all of you computer scientist gamers out there, but still worth mentioning. So here we have this main loop that we've been talking about, and if we happen to do 60 of those per second, then this is running at 60 loops per second, or because each loop contains a render, then that is 60 render calls, so 60 frames per second. Typically, when we talk about frames per second, we're talking about the number of render steps per second, not the number of update steps per second. Because we technically could put as many update steps in here as we want, right? We could put a loop in here that does it 1,000 times. So we're talking about frames per second, typically talks about the number of renders per second. Okay, so graphically, intuitively, we would want as many renders per second as possible because it just looks smoother, right? So it would be great if the gameplay were as smooth as possible, unless you have some sort of game mechanic that you don't want to be smooth. I don't know, maybe your chess engine doesn't want to be as smooth as possible. I don't know. So this frames per second typically is determined by 2 things, and those 2 things are quite related. So it's how much work that you're actually doing in a loop, like how many CPU cycles you need to do that amount of work, and how fast is the underlying hardware. It's a ratio of those 2 things, right? So if you're doing, let's say we have some magical count of work, like I'm doing 100 work, and my CPU is 200 per second, then I can do 2 of those things per second, right? It's pretty obvious. Older games had the advantage of knowing the exact hardware that they were running on. right? So if you're coding for the NES and you make a game, you know, okay, if I plug it into that NES, it's going to be running at the exact same speed. If I plug it into another PS5, typically it'll be running at the exact same speed. Now, with modern games, you may have things like hard drives that are at different speeds. Maybe you could upgrade the RAM or the video card in a console, I don't know. But typically, it'll be running at about the same speed. But the difference here is that modern computer games must run on a variety of hardware. So we have to worry about that, which sucks, because, you know, the more work we have to do as a programmer is kind of annoying, but it's part of the job, we have to do it. So this flexibility can depend on a bunch of different things, right? So how fast do I want this to run? We have to look at the hardware of the machine that we're running on in order to be able to determine what can we actually do to affect that. So for example, maybe our operating system only allows us to input 10 things per second. Right? So trying to get user input at 60 frames per second may not be possible. Now, these are things that you used to have to worry about, but not so much anymore. Are hardware input events blocking? Or are they non-blocking? Right? Things like this. Maybe my monitor, maybe this software has to be running in VSync, which means that my frames per second physically cannot be higher than my monitor's refresh rate. Right? So that's another thing, okay? This game is it going to be running at a different speed based on the price that someone spent on their monitor? And yes, like ideally it will, because you'd want to be able to play it at 200 frames per second if you have a 200 hertz monitor, or 60 frames per second if you have a 60 hertz monitor. Networking. Now, we're not going to be talking about networking in this course because it's a whole like PhD thesis. I'm not even going to get into that. But the type of traffic, timeouts, packet loss, whether or not you're doing all sorts of crazy like prediction or catch up or whatever in your networking code, that can all have effects as well on the physical things that you can do in the code to affect your game loop speed. But let's say we're running on modern hardware, no networking concerns. We've got a monitor that can do at least 60 frames per second. That's a reasonable assumption in today's gaming world. So let's just say we want to fix the game at 60 frames per second, and we don't have a function in SFML to tell us how to do that. So of course, we can just do this with our window.setFrameLimit in SFML, but let's pretend that we didn't have that. So to do it manually, we have to limit our game loop to run at most every approximately 16 milliseconds. So here we're talking about per second. So there's 1,000 milliseconds. I could have chosen nanoseconds here, but typically when you talk about gaming speeds, you're talking about millisecond level. So 1,000 divided by 60 is like 16.6 repeating milliseconds per frame. So what we're going to have to do is first and foremost ensure that our code actually runs in 16 milliseconds, right? So if we take our user input code and our update code and our rendering code, well, if that doesn't run in 16 milliseconds, then there's no way we can actually run our game at 60 frames per second, right? Get good, optimize your code a bit, or scale back on the amount of graphics or processing or whatever. But let's just assume that we can run all of our code in under 16 milliseconds. Then if we just let the game loop spin as fast as possible, we have that problem like before, right? Where your computer might be running 1,000 frames per second, yours, sorry, is 20 frames per second, right? You need a new computer. So what we do is we add this what's that?
I am actually going to upgrade my PC next month.
Based on what I said? Yeah. So we do have to put in this artificial delay, right? So we process the input, and this slide here comes from that game programming textbook that I was talking about. So we process the input, we update the game state, we render, and then we add some delay. Okay, let's look at that in code. Now this is, not exactly C++ that will compile, but it's close enough. It's pseudocode. So first, determine how many milliseconds that we have per frame, right? So maybe you have a target in mind. Your game designer has said, okay, we're targeting it for this version of the Xbox. You couldn't pay me $100 to tell you what the newest Xbox is, like their naming scheme. What is the newest Xbox?
Series X, and then There's the cheaper Series S, I think.
Okay, so anyway, I don't know what Microsoft is doing, but just put a number at the end of it, please. So I'm targeting it for this hardware. That hardware can do this. Most TVs are 60. Okay, we're going to target 60 frames per second. So you've decided this. As a game programmer, you haven't decided this. The person who gets paid more than you has decided this, right? Then, in your game loop, you're going to somehow record the computer clock's start time. So before you start doing any work on this frame, you record the start time, you process the input, you do the update, you do the render, and then you calculate the current time, and you subtract it from the start time, right? That's typically how it happens. Now, I remember when I first started programming, I was like, how do you time stuff like this, right? Like, how do you time events in a computer? Is there like a stopwatch that's always running and updating? And then I was like, oh, there's this weird effect of if you're timing something, doesn't that actually take longer to run if you're timing it, right? Because you've got to have this stopwatch running or whatever. But it turns out that, you know, you just record the time and subtract it from the other one. There's not some big update going on. But yes, it is true that there's this weird not quantum like as in quantum physics, but there's this effect of if I want to record how long something is taking, it will take longer to do it because it takes time to actually measure the time. Imagine you're running in a race and you have to keep looking at the clock, like that affects your performance, right? So we calculate the amount of time that has elapsed and we take the maximum amount of time per frame that we're allowing ourselves, we subtract the elapsed time. And who can tell me why I'm putting this max here? Hand up. Just think about it for a second. Why am I putting this max 0 before that? Why would that ever be negative? As soon as I say it, you'll slap yourself. Okay, so I'm saying I want to max this with 0. Because, well, I don't want to sleep for a negative amount. I just don't want to pass in a negative. It's possible that if I pass in a negative here, sleep will just say, oh, and by the way, sleep is just like a way of halting execution for a bit, right? Every programming language is going to have some sleep. It just takes the current process and it does nothing for a certain amount of time. Now, it's possible I didn't need to do this max because I didn't want to pass a negative into sleep, so essentially, if elapsed is greater than milliseconds per frame. Like, how would that be negative? Well, if I'm subtracting one from the other. So if my game update, if my game engine is too slow, then that value is going to be negative, right? But typically, we've assumed that it won't. And so let's say that our code took 5 milliseconds to run. Then milliseconds per frame is 16 minus 5. Okay, so that's 11. So now I've got to do nothing for 11 milliseconds here. And that's literally what's happening. It's that simple. If this was 20, then I'm 4 milliseconds behind, and so I'm going to see the gameplay is going to be a bit slower in my game. So adding the sleep at the end of the loop ensures that the game won't update too quickly, right? So we can set a maximum FPS, but we can't set a minimum FPS. I talked about this briefly earlier, but there's no way to ensure that your code is fast enough to be done in the amount of time that we want to do it in. The only way to do that is if you actually go and optimize your code. So, you know, how do I know when I'm writing my game engine when to stop optimizing? Like, if my game engine, okay, I'm running it on my PC, I've got a development machine, it's pretty fast. I run my game, I profile it, which we'll talk about a bit in another lecture. I see that each of my updates is 14 milliseconds. Perfect. I can run at 60 frames per second. But that 14 milliseconds running on someone else's computer might be 20, might be 30 milliseconds, right? So you got to leave yourself, like, if your game code is running in more than just a couple of milliseconds, it's probably the case that, you know, but anyway, you test it on a bunch of hardware. This is why you have QA at your company. You test it on a bunch of things. They say, oh, it's running slow on my machine. You keep optimizing. So in this case, you have to cut some computation or optimize stuff to make it run faster, right? There's no command that you can run that just says, make my code run faster. All right. So this can have a potential problem, and the potential problem is this. This could be too slow sometimes. Typically, your input processing is not going to be too slow. This could be too slow if you've got like a bunch of physics or AI or whatever running in your game. This could be too slow, and so in that case, I don't know what to tell you, right? You're just going to have lag in your game. What SFML does, I want to read this out because I want to show you just how similar this is, but also some caveats of using the SFML system. Set frame limit on an SF window sets the frame rate to a maximum frame per second. So if this limit is set, the window will use a small delay after each call to display to ensure that the current frame lasted long enough to match the frame rate limit. SFML will try to match the given limit as much as it can, but since internally it uses SF sleep, whose precision depends on the underlying operating system, the result may be a little unprecise as well. So for example, you could get 65 FPS when you're requesting 60. So just be aware that these calls to sleep, etc., depending on the operating system, depending on the hardware, may have different resolutions. The clock on one operating system or piece of hardware may be valid down to the nanosecond, probably not, but very close, or microsecond probably. Another one may have millisecond timing, right? So you've got to keep that in mind when you're making your games. So I'm going to talk about, in a few slides, ways of sort of, if you do have lag, where a couple of frames may be too long, what you can do to like alleviate that problem. In some cases, you want to do this, and in other cases, you don't. So what do I mean by this? So let's picture a game that's running, like, okay, it should be running at 60 frames per second, right? So I've run it on a bunch of different hardware, and, you know, Link is running across the screen, and it takes him 10 seconds to cross the screen. All my testers and everyone says 10 seconds is the right amount of time, right? Then I run it on some other hardware, and it actually takes 20 seconds because that computer is really, really slow. So what do I want to actually happen on that computer? What do I want that user to experience? Do I want to just do nothing and have it be really laggy? Do I want it to sort of process a frame and then sort of catch up somehow? Like, what do I want to happen, right? And so also, there are cases where your computer, and this is probably what's going to happen in most cases, my computer is completely fast enough to run the game, but then, I don't know, McAfee starts running in the background, and I get a few lag frames, right? So there'll be a few frames where it takes longer, rather than, if your computer is so slow it can't run it fast enough, you're just kind of doomed from the start. But let's say the computer is fast enough, there's a few lag frames, how do I want to deal with that? Do I just want it to, like, appear slow for a bit, or do I want it to catch up to where it should be if I was running fast enough? And the thing is, that's a decision, that's a gameplay decision, right? It's a game design decision. As a game programmer, you just take what the game designer or the gameplay designer told you and you implement it. But depending on the game, depending on if it's a network game, you would probably want to catch up to the point where the other player is. If it's not, then maybe you're just okay seeing it run slowly for a few frames. And the slides are essentially, that I'm going to show, are a bunch of like separate ways to handle the problem. It's not like do this one, then do this one, then do this one, or the first one's the best, or the last one's the best. It's just a bunch of different ways that you could tackle this issue and try them and see what works for you. So neither of these are the right way, but I'm going to say a few of them and then say what the pros and the cons of each one might be. But again, what you do here is dependent on the gameplay and the game design. So one is called game simulation scaling. So the problem we face is the following, and this is a bit of a repeat. Each update advances the game time by some amount, right? It takes some amount of real time to compute that. If 2 takes longer than 1, then the game slows down. And ideally, we don't want the game to slow down. So for example, if it takes longer, and let's say, you know, we're programming some game and we want the game world's timer to run at the same speed as the real world timer, right? So that's what we're trying to match for whatever that means. If it takes longer than 16 milliseconds to update the game by 16 milliseconds, then we can't keep up. If we could advance the game world by more than 16 milliseconds, we can update less frequently and keep up to date. Okay, what does that mean? Well, it means what we can do is we can introduce a variable that we will use to update the game world simulation. And this is called a variable time step. So let's say, for example, in our game update function, instead of just adding, let's say we say Mario's speed is 5, right? Or Mario's speed is 10. On each frame, what we're doing there is we're just saying Mario's x position plus equals 10. We're taking the velocity and we're adding it to the position. There is no concept of time there. It's just one update, one update, one update, one update. What this is saying is we can input an amount of time that we want to pass in the game. So for example, okay, Mario's speed is 10, maybe that's 10 units per second or whatever, but that doesn't mean that Mario is always going to move 10 per frame. Maybe I'm going to have some variable that I pass into the update function that says, update the game world by 10 milliseconds, or update it by 50 milliseconds, or update it by 5 seconds, right? And so I can do this, I can scale how much things move based on this input. So here, what happens is, and one way of doing it is to calculate how much time has elapsed from the last frame. So how much time did the last frame take to compute? And then, on this frame, I'm going to pass that elapsed into the update function. So what happens here is that if my last frame took 16 milliseconds to compute, then I'm going to update my game world by 16 milliseconds. But if my last frame only took half a millisecond to compute, then I'm going to update my game world by half a millisecond. And ideally, in a perfect world, this would just work, right? So now I don't even need to put this pause at the end, because this can run at a variable frame rate, and it just adapts to whatever my frame rate is, right? So I can run this loop as fast as I want, and on a faster machine, it'll just mean that each time we update the game world simulation, on a faster machine, Mario will just be moving by smaller increments. On a slower machine, Mario will be moving by larger increments. But ideally, they'll be moving at the same relative speed, right? So that's an interesting idea. Each frame will calculate how much real time has passed since the last game update, and then we pass that into the simulation as a sort of scale variable, right? So we multiply everything that takes time into account by this scale variable. And so, for example, with a bullet flying through the air, each time step, update it with its velocity, but with the variable time method, you scale the velocity with the amount of elapsed time, right? So your speeds now would no longer be unit of measurement per frame, which is what we're doing in our course. It would be instead unit per second or something like that, and then we would multiply it by the amount of seconds that had passed since the last frame. Now the advantages here, in an ideal, you know how physicists, if you've ever taken a physics class, it's like, okay, we're going to do some word problem, like how long does it take a chicken to fly, you know, from one side of the road to the other, and they make assumptions, right? Like, okay, chickens are perfect spheres, there's no air resistance, and there's no friction, right? So in those worlds, everything is great. And so this is that example here. Like, the game is going to play at a consistent rate, meaning that, you know, everything in the game is going to move and interact at the same rate, like the same speed on the screen, no matter what. But if you have a faster machine, it's just going to run at a smoother frames per second, right? So in an ideal world, this is exactly what happens, and this is perfect. However, these are computers, and computers are not perfect. The disadvantages is that based on a multitude of factors, you may actually get inconsistent effects based on this variable frames per second. What do I mean by that? Well, if you've ever had to do anything precise with floating point numbers, you'd know. Like, for example, someone give me a floating point number below 1 that can be perfectly represented in computer hardware? A half. Why? Yeah, right? Well, more accurately, it's the sum of powers of 2. It is, but there are numbers, like you can also represent 3/4, which is 1/2 plus 1/4. So in any computer system, the only numbers you can represent exactly are sums of powers of 2, right? Because they've got to be, they're binary, so integers are all fine, right? The integer part of any floating point number is fine. Well, okay, if you get really large, then you get weird things. But you cannot, for example, 0.2 cannot be represented exactly with floating point numbers. It's going to be like 0.200000008 or whatever. So just go into any programming. Now, some programming languages have ways of working around that and representing them in different methods, but floating point, C++, there are some numbers we just cannot represent exactly. And that leads to floating point errors. So if your frame ran in 0.2 seconds, it cannot accurately represent 0.2 seconds. And then that 0.2 is going to be multiplied by some value, maybe the speed, and then your value is going to be slightly off from my value. And you might say, okay, why does that matter if it's only like 0.0008 off? Well, because that 0.0008 may be the difference between a collision happening on that frame and a collision not happening on that frame. But that's not even the worst part. If you have a network game, you may have network desynchronization based on variable frame rates of the 2 game simulations, right? Because in my game, that collision happened, but in your game, that collision didn't happen. Or the weird thing is, if your computer is too slow now, maybe you can actually pass through a wall. How does that happen? Well, if the game time elapsed is so big, and that's what you're multiplying by your speed to get your new position, on faster hardware, you're moving at smaller increments. But on slower hardware, you're moving in larger increments, so maybe you can pass through that block. So you've ever, I watch a bunch of speed running, and in some speed runs, they have to modify the frame rate in order to get a particular glitch to work. And this is one of the reasons for that can happen. It's not always going to happen in all games, but you might say, okay, now he has to do the clip where they move backwards through a wall or whatever because there's no capped back speed, but at 120 frames per second, the updates are too frequent, and so it's not going to clip, so I'll set my frames per second to 10 just to clip through that wall and then set it back for the rest of the game. Like, it's weird, but that does happen. And of course, physics simulations, collisions, whatever, they could all be a little bit different. So yes, it does have these advantages, but the disadvantages are that you have all these inconsistent effects. And one of the interesting thing is, if you get into like research or physical simulations like fluid dynamics or modeling explosions or heat equations or whatever, you do actually, this is the way that people do those. They are typically not fixed time steps calculations, but they are, okay, I'm going to choose some time step to perform between iterations. Sorry, okay, I want to clarify that because what I said was technically incorrect. In physics simulations, you are not doing this thing where you see how long the previous calculation took and then vary the time step. You are just picking a fixed time step. So if I wanted to do a physical simulation, it's different from a video game. You just run it on some supercomputer, right? You don't really care how fast it's running, but you do have to pick a time step. And my point here was that this actually happened to me, so I'll just tell you the example. I had a robotics simulation where robots were being represented by just circles, right? And so I could control one of these robotic circles, and there were other circles representing like dirt that I wanted to move around, right? So I could drive this robot around, it was a circle, and these other circles, I would bump into it and they would move. And the point of this simulation was to try and like corral the other circles to move dirt around into some pile or whatever. And what happened was, okay, I picked a time step update, let's just make up something, of like 0.1. So I would multiply all my distances by 0.1, and then I'd run my simulation. And so let's say that my simulation, okay, 0.1 seconds per update, and I wanted it to run for 100 seconds. So 0.1, that's 10 per second, 100 seconds, that's 1,000 simulation steps, right? So I ran it for 1,000 simulation steps, and I get some number, and that number is my error or whatever. Then what I did is I said, okay, let's run it 10 times as slowly. So 0.01 per update. So now instead of 1,000 time steps, I need 10,000 time steps. Now, all the code is the same, all the physics is the same, all the equations are the same. It's just that instead of moving stuff by 0.1 in time, I'm 10 times moving it by 0.01 in time. So again, where all the chickens are spheres and there's no air resistance, this would just work, but I got a drastically different result. And it turns out in a lot of these equations, there are, this is a very big thing and there's papers written on this and like, what is the time step that we want to choose such that these mathematical errors don't happen, etc. So just keep in mind that that stuff can happen based on the choice of these variables. So yeah, that's this variable time, that is the problem that can happen here, that we could have a number of different types of error because 1, floating point errors, and 2, these variable number of updates that are happening. So how does rendering fit into all of this, right? When I actually draw stuff. It turns out that how and when we render is not super important. Because whether or not we use variable time steps, rendering is just sort of its own thing, right? You just update the game state, and whatever the game state happens to be, I'm just going to draw it to the screen, right? So if you did an update in 0.1 seconds, if you did an update in 2 seconds, doesn't really matter because the rendering is just going to draw it to the screen. So instead of variably updating the game simulation, maybe we could try rendering at different times. So far we've just been talking about the update. What could happen if instead of doing that, we rendered at different times instead? And so this lets us get back to fixed time steps. And by rendering, I'll show you what I mean by this. So by rendering at different times, that's actually sort of a bad way of explaining it. So forget that I said that, and I'll update the slide for next time. Here's what I meant by this. Instead of changing the amount that things change in a single update, let's do instead a different number of updates. But each of these updates is now going to be fixed, right? So we're always doing the update with a fixed time step, but we're doing a variable number of them. Okay, why would we do that? And so what can happen here is that this is a method that, let's say, we had some lag in the game, and now we're behind where we should be. Here, I'm going to do multiple updates to catch up the game state to where it should be, and then the next time I render, we're essentially caught up, okay? So here's my analogy. I'm very proud of this analogy, and I have a diagram. It's so good. So let's say that you are tasked to make a cheeseburger every minute at a fast food place, right? So I know this is a bit of a juvenile example, but I think I still like it because it helps me keep track of this stuff in my head. So this is your frames per second that your boss has told you, right? Like, we're the game programmer, the game designer has said, whatever you do, hit 60 frames per second. In a different world, you're working at McDonald's and the boss says, whatever you do, you're making 1 burger per minute. But the good thing is, it only takes you about 15 seconds to make a burger, right? So you've got 45 seconds to sleep between each burger that you make, or chat with coworkers or whatever. Now, what happens? Disaster. 1 burger slips out of your hand and it falls on the ground, and you got to clean it up because you can't have burger on the floor. People be slipping on it and everything. But it takes you 2 minutes to clean that up. This is our lag analogy. One of our frames, for whatever reason, McAfee came in and knocked all your burgers on the floor, right? Or your network lagged or whatever. So you're behind by 2 burgers. And burgers, you're not making floating point numbers of burgers, right? You are making discrete burgers. And so since you can potentially make 4 burgers per minute, just make 3 burgers in the next minute. And now you're caught up, boss is happy, mess is cleaned up, whatever. So here is our desired burgers per minute, right? So frames per second becomes burgers per minute. So here I've got my burgers, 60 seconds apart. This is what I want to hit, ideally. Now, I actually don't, the cool thing is this actually does have analogies to gameplay. Because even if I could do it faster, I don't want to do it faster. I want to do it as close to 1 per minute as possible. In a fast food restaurant, it's because you don't want to have 50 burgers waiting there getting cold. The customers will complain, right? In a game, like you don't want things updating too fast because then it gets weird stuff on the system, right? So you want to definitely match it as closely as possible. But, like I said, it only takes us 15 seconds. There's a little red here, it might be hard to see in the class. It only takes us 15 seconds to make the burger, and I have 45 seconds to rest. I'm sure you know where this is all going, but here was an accident. I lost that burger, right? I lost here. So there's 120 seconds where I've done nothing, but on the next one, I can make up those 2 burgers that I missed and be caught up, and now I'll be here. So here's the McDonald's manager's choice. Do they want 3 burgers to be made in that minute to be caught up? Or do they just want 1 burger per minute after that? And that's the game designer's choice as well, right? Do you want to be caught up and have this because what you're going to see here is kind of weird, right? Imagine you're in the burger place and you only open your eyes once every minute, right? So if you only open your eyes once every minute, you see, okay, burger, burger, burger. Okay, no burger, no burger. What's happening? This is weird. That's the lag. And then you open your eyes and you see 3 burgers, right? But then it gets back to normal. So do you want to actually be behind in the game and just see a bit of lag so it just doesn't render for a few frames? And if that happens, do you want to skip 3 frames and go to where you would be if the lag didn't happen? Or do you want to just continue on making 1 burger per minute after the lag happened? There's no right answer here, right? It's all up to you in how the game performs. So this is the pseudocode for that, right? Up here, we've got the current time. We calculate elapsed. Then we just store the previous so we can do this again next frame. Then we're keeping a running total of the amount of lag that we have. So lag, we're going to add the amount of time that we elapsed to the lag. And if elapsed was bigger than lag, then that means we'd have to make multiple burgers, right? So we process our input and we say, while lag is greater than milliseconds per update, then down here, we would do any amount of updates that we would need, right? So if our lag from the burger example was 2 minutes, then here we would make burger. Okay, I've caught up 1 minute. We've still got 1 minute left. Make another burger, right? And then make that final burger for this frame and then go on. And so what does this do? The lag measures how far behind the game's clock is, behind the real world clock, if that's our analogy. The inner loop is going to update the game to catch up until all the lag is gone with fixed step updates. And, you know, in this case, the fixed step updates are, I'm going to add 2 and then 2 and then 2 and then 2, right? So I'm sure that this is not going to have any undesirable floating point effects, etc. Once we catch up, we render the scene. And so the game simulates at a constant rate using fixed time steps in a safe way to catch up for these lag frames. And the rendering may appear to skip, right? You skip ahead to that 3 burgers while the game catches up, but at least the simulation speed is fixed on different hardware. And so we can only catch up if these lag frames are infrequent. So let's give an example where you might not want to do this. Maybe you don't want to do this because you're okay with it just lagging for half a second and then the user continue on. But maybe this game, I don't know, it's like Celeste or some high-performant platformer, and you've got a bunch of people speed-running the game, right? And if there is lag, you would like the player to be caught up to where all the other players are, or something like that. But if I go back here, this pseudocode is kind of incomplete. Can anyone say or figure out what might be an issue here with this particular method of updating? And I'll give you a hint. An infinite loop could happen, and we would never render again. Why might that happen? Okay, so because time is running out, if this update takes longer than milliseconds per frame, right, then we're never really escaping this. So that would be bad in the way that I've written it here. So just be careful. You might want to say, okay, there's some maximum number of times that I want to try and catch up, so that if I did have a huge lag frame, I'm not skipping ahead by too much or something. Okay, so now what we've done is we have removed the synchronization between game update steps and rendering, right? We could do, instead of just update, render, update, render, update, render, we could have multiple updates per render. So we no longer call render once per update. This means that we could, in theory, do something like put the rendering into another thread, right? So if, modern games are going to be multi-threaded, they're going to use all your processors in fun ways. And so we could have the game simulation just happening over here and the rendering happening over here in another thread. I'm not getting into multi-threaded game architectures and what could arise, but issues can arise from this. And you're going to have to, it's not just as simple as putting them in different threads and everything is solved. For example, you could be rendering between updates, right? So, okay, it's going well. So if I've just got my updates running as fast as possible, and my renders running as fast as possible, okay, here it took 2 updates before the next render, but look, here, maybe this render didn't take as long. And so now we're rendering between 2 update steps. So now do we have to do something where we have like, I don't know, like a lock that says we can only render after an update has just been performed? Or do we have 2 copies of the internal game state so we can always refer to the previous one, right? Because if we render while these variables are changing, well, this isn't thread safe and a bunch of things could change and like, I don't know, lots of different things could go wrong here. And ideally, this is not what you want to do just straight out of the box. There's lots of considerations here. So don't just try and implement this and hope that it all works out, because there's a lot of things that you would have to do to make sure that this doesn't happen. So if we render between updates, the game world could be the same for 2 frames, which could be choppy or bad. You could be like rendering, and let's say the player's position when you start to render is different from the player's position when you end rendering, and so should you taken it here or there, etc. Lots of weird stuff can happen. What some games actually do, especially when lag is caused by networking problems, is they actually have like 2 game updates. One is like the actual game update of everything once all the network information comes in, and another one is like a local only version that uses things like, okay, what speed was I running at the time when the lag occurred? What was the bullet flying when the lag occurred? So we're going to take what was happening, and while I'm waiting for more network packets, I'm going to simulate what would have happened locally. And then when the network catches up, I'm going to change it, right? So this can be called rollback. Like there's lots of different types of net code that can happen. Now, we're not going to get into that in this course, but it can be very, very complicated and have dramatic effects on gameplay. And the reason this happens is because an example that I have is back in the day, I used to play Quake on dial-up. And my ping in the game was literally half a second. So we're talking 500 millisecond ping, right? And in the original version of Quake, before Quake World came out, which changed the way the netcode worked, is that if you pressed forward, it sent it to the server, which was the other person's machine, essentially. And then you didn't move until you got the reply. So if I pressed forward on my machine, and I have a 500 millisecond ping, I literally wouldn't move forward for half a second. if I shot, I literally wouldn't shoot for half a second, right? So you got very good at like starting to turn a half a second before you actually had to turn, or jumping a half a second. Like, it's obviously bad, but like you could get a lot better than you think at predicting based on stuff like that. Now, obviously you just lose. And there was literally a term, LPB. Does anyone know what LPB is? Thankfully, you're all on, you know, like at least cable modems, probably fiber. But LPB was a salty term that we used to use called low ping bastard, right? And so why did you lose? LPB, right? Because his ping was just lower than mine. But I mean, you know, you play with people in California at a half a second delay and they've got like a 20 ping or whatever. It's, anyway. So the physics may not be exact for that render, but the game world would be exact in the future. So in the Quake example, with the half-second delay, what would happen is I would issue a jump command, and it would literally jump immediately on my machine, right? The other person may not see me jump until they get the network packet, but then it would try and synchronize somehow, right? It was a mess, and it led to bad gameplay. One way that fighting games, since fighting games went online, one way that they do rollback is, let's say I do some move that has like a third of a second animation, right? So some like jump kick or fireball or whatever. So what can happen is fighting games have a kind of, they have it hard and easy. But one of the ways they do it is I'm going to do this move that has this like wind up or animation. I send that packet to the server. The other player's client realizes they sent this packet 10 milliseconds ago, and they're doing this move at this position. So what they can then do is maybe skip the first 10 milliseconds of that animation, right? So the same move is being performed. They've just skipped the first part of it. And anyway, you can see how, like, it's just to try and get them as synced up as possible. There's lots of different networking tricks that you can do, and this is the reason for doing all this. But why does all this matter? Well, it matters in ways that you may not imagine, but I've already covered this, so you do know it. Given our basic way, and this is actually something different now, so this is kind of a disjointed topic. So given our way of doing collision detection, an entity going fast enough could pass through a game tile, or a bullet could pass through a tile or whatever, right? And so we fix this in assignment 3 by setting a maximum speed for entities. So for example, the way we do collisions is to check where things are right now and to see if they overlap, right? That's the simplest possible way, and it's the way most games do it. If you think about, okay, we want to be as accurate as possible, we could do something like take our current speed and our current heading, look at where everything in the level is, and then calculate, based on my current speed, when a collision would occur, right? And then maybe if I get close enough to that time, I can just make the collision occur, etc. But stuff like that is so complicated, and it leads to inconsistencies, and it's also very slow. So we typically don't do that. We typically just do the check right now, is there a collision right now? But if the speed is bigger than an object, I could pass through the object, right? Because I check it on one side, it's fine. I move it, I check it on the other side, it's fine. So this is how 99.9% of all out of bounds or clipping in games work, is that that distance that you have moved is just wider, it's further than the width of the object that you pass through. We did a janky thing in assignment 3 by setting a maximum speed for our entities, right? So I could only fall at like 20 pixels per frame, and all my stuff was 64 pixels, therefore I can never fall through it. But in Super Mario 64, the way you can clip through stuff is that they set a maximum speed in the forward direction, but they forgot to set a maximum speed in the backwards direction. So you can go faster and faster and faster backwards and eventually build up enough speed to pass through stuff. As long as the maximum speed is less than the thickness of the smallest tile, then this works fine. This might be janky, but it works, right? But what if we wanted, for example, our bullets or entities in the game to actually be able to go faster than that, right? We have a bullet. I don't want to be like a hit scan instantaneous bullet, but I want this bullet to be really fast, like get through the screen in maybe half a second. And in order to do that, it's got to go further than the width of a tile every time I render. And that's just it. Like the player will see it here, and then they'll see it over here. But is there any way that I can have that happen? Have a tile in the middle, but it still collide with the tile? Well, turns out that we can do that. And that is by doing multiple update loops. So one simple solution is to increase the number of game ticks per second, right? So example, we want the max player speed to be 100 pixels per frame, but a tile is actually 32 pixels wide. So we'd have missed collisions everywhere. So what we can do is instead, let's take 100 pixels per frame, and then we'll just choose based on, for example, how fast it takes us to actually update the game simulation, right? So if we've got lots of time and we know that we could do 4 full ticks of simulation in the amount of time that we have between renderings, then instead of having it be 100 pixels per frame, we could do 4 separate updates of 25 pixels per frame. So if we do 1 update per render at 100 pixels or 4 at 25, it's going to look identical to the player. They don't see the game updates happening in the background, right? They only see the end result, which is when it's rendered. And so we are trading CPU effort for simulation accuracy. And whatever the universe is doing, you know, if time is continuous or if we actually move in really discrete time steps in the physical universe, that is what we would want to do. We would want to do millions of game tick updates per second to get the most possible accuracy, but we can't do that. And so we have to, through testing and profiling, we guess, okay, how many can we reasonably handle and do that reasonable thing? And here's that illustration, which is now probably pretty obvious. But let's say we have Mario here moving, and this is our game speed. So our game update happens once per render. And so here, Mario is here, gets rendered, Mario gets updated to that. So Mario's position, just pretend that Mario is right here, gets rendered, Mario is right here, gets rendered, here gets rendered, and then here gets rendered, and oops, now they're on the other side of the pipe, right? So what we could do is we could say, oh, okay, I can afford maybe 4 of these per update, and so instead of having 1 update per render, now I have 4 updates per render, and oh look, now I've collided with the pipe. And so Mario will be to the left of the pipe instead of erroneously to the right of the pipe. Okay, so there are 3 YouTube videos here, all made by the same person, Pan and Coke on YouTube, who does like insane, I don't know how a person can love a game this much. But their whole channel, I guess if you're making money from YouTube, it makes it different. But these videos are all excellent. I think that this video is the most relevant, and it is how the physics work in Mario 64 for the Super Nintendo. And you know, before we had game engines that could run on any hardware like Unity or Unreal or whatever, you had to come up with your own physics engine. For every new game basically had its own physics engine based on the gameplay mechanics. And this video is truly excellent. I'll put them, you know, so you can click on them, but I'll also put them in the timestamps in the video. But what I'm going to do now is I'm going to play the first video because it's short enough and we have enough time and I think it's interesting. I'll play that in class, but I'll cut it off from the video. So the actual video for people not in the class will end now, but we'll stay in class and we'll watch this first video.